Hello,
Hello.
hello everyone.
Hello, everyone.
So, hello everyone. Just hello. Yeah. Hello everyone. I am Himanshu Mishra, and in this week we are going to solve the question from dynamics. So until now we were solving the question which were based on the statics. So we looked the concept of equilibrium, and we used that concept uh, in various applications like truss, beams, frictions, and so on. We solve various problems based on the equilibrium, whether they are moving or not moving. But in those problems we were concerned only about the forces, that how the forces uh, change the overall condition of equilibrium in the system. We were not concerned about how those forces change the motion, or how the motion will going to change the force. So we have given few forces, and we have been asked to find the remaining forces which make the system completely in the equilibrium. So from this lecture we will be talking about the dynamics. So basically there are two parts in the dynamics: kinetics and kinematics. So we will start with the kinematics, where we have given the motion, and we have been asked to find the or analyze the motion quantitatively. For example, let's say we have given the distance, and then we have to find the acceleration and velocity, or we have given the acceleration and we have been asked to find the distance the particle will reach at some certain time, or when it reaches some certain velocity, and so on. So in today's lecture we are not going to concern about the forces, because in the kinematics, given any of the quantities like distance, velocity, and acceleration, we have to find the other quantities which describe the motion, which are same, velocity or acceleration. So for example, if you have given the acceleration, you have to find the distance or velocity at some time or at some distance. You have given distance or velocity, you have to find acceleration at some time or at some distance, and so on. So still we are not going to concern about the forces, but in kinetics what happens that you have given the force, and then you have to describe the motion, that with this force what is the velocity or what is the acceleration. Or you have given the motion, description of motion, for example you have given the acceleration or the velocity, and then you have to find the force, like that. So this is kinetics. So in the kinematics you don't need to concern about the forces. So we will be starting with the very basic concepts of the kinematics. So we know that the velocity can be given by change in distance divided by change in time. So this velocity expression can be written as ds by dt. So here v is the velocity and s is the distance. Similarly, the acceleration can be given by change in velocity with respect to time. And I can write the acceleration as in terms of distance also. So it could be dv by dt, which is change in velocity with respect to time, or change, or it's a double derivative of the distance with respect to time. Now from this expression and this expression, we can actually remove the time component, and when we solve this together we can actually write the relation, which is v dv equals acceleration ads. I can write this as v as s dot. So this can be written as s dot, and this can be written as s double dot. So s dot means the derivative of s in time, and double dot means double derivative of s in time. So this expression can be written as s dot ds dot equals s double dot ds. So this is one of the different convention you can follow to write down the equations. So there are three popular equations you might have come across when you study the kinematics. So basically those three equations usually derive from these expressions only. For example, let's say if I consider this expression, or let's say first consider this expression. Okay, I can write this expression as dv equals a dt. Let me integrate from v0 to v and 0 to time. So you can see the left hand side is integrating from v0 to v. We are integrating the velocity, and the right hand side we are integrating the time from 0 to t. Now assume that my acceleration is constant. This is the assumption we are making. So we are going to write down the equation for those cases where the acceleration is constant. So what we can do, we can actually put this acceleration. So here acceleration is constant in time, okay, or it is also constant in space. So the main motivation to follow this assumption is we can write down this acceleration outside of this integral. So we can write this equation as like this. This is for the constant acceleration case. So when we solve this integral, we will get v minus v naught equals at. So we will get v equals v naught plus at. So this is one of the relation of velocity in the case we have given a constant acceleration. So you have given the constant acceleration and you have given the initial velocity, then at some time you can actually find the final velocity. Then you can use this expression also. Now again we are assuming that the acceleration is constant. So in that case, so I am integrating from v0 to v at left hand side, and at right hand side I am integrating from s0 to s. So if my acceleration is constant, I can write this as, I can actually pull out the acceleration outward to the integral, and this can be written as, when we solve this equation taking the integral, we will get v square equals v0 square plus 2a s minus s0. So this is the second equation of motion given that my acceleration is constant. So here you have given the distance, initial distance and some final distance, and you have to find the velocity. So in the first expression you have given the acceleration and you have to find the velocity at some time. In the second expression you have given the displacement, initial and some later displacement, and we can find the velocity by this knowledge, final velocity. Then if we can use this expression here and this expression together, so my v equals ds by dt. This I can write as ds v dt. So v dt I can write using this expression. So here v equals v0 plus at, right, or this expression. So this will be v0 plus at dt. and using the same assumption that we are following, my acceleration is constant. This I can write as, after solving the expression or integral, I can write this as s equals s naught plus v naught t plus 1 by 2 at square. So this is my third equation. So these are pretty famous kinematics equation that you can follow. The only thing you need to keep in mind when you are using this equation, that the acceleration should be the constant, which means acceleration should not be a function of space or time. It is always a constant or a number or a scalar, right? But what about those problems where the acceleration are not constant? So in those cases, what happens that you cannot put this acceleration outside of integral. So you need to integrate the expression of acceleration, because let's say my acceleration is given by 0.5 t square. This is my acceleration. So you can see here the acceleration is not constant because it is dependent on time t. So as the time increases or as the time is passes by, my acceleration is also increases. Because my t increases, it makes my acceleration also increases, because it is proportional to t square. So you can see you cannot put this acceleration outside of integral. So you have to integrate the expression of acceleration, which is 0.5 t square dt so it will be 0.5 t cube by 3 when you integrate this. So you will not get this kind of an expression, but it is still you can able to solve problems where acceleration are not constant. You just need to integrate the expression of integral to find the required velocity and the distance. That's all. But if the acceleration is constant, then instead of using the integral, you can use these expressions, the equations of motions here, this three equation of motion that we have derived. Right, so let's solve few problems based on the concept we have discussed, and then we will move to the curvilinear and the polar coordinate, where we will be finding the velocity and the acceleration in the polar and curvilinear coordinate. But before moving to those concepts, let's solve the problem based on this, whatever we have discussed now. So in the first problem, we have given the velocity of a particle which moves along the s-axis is given by 2 minus 4t plus 5t 3 power 3 by 2, where t is in seconds, v is in meter per seconds. Evaluate the position s, velocity v, and acceleration a when t equals 3 seconds. The particle is at position s naught equals 3 meter when t equals 0. So we have given the velocity expression, which is 2 minus 4t plus 5t 3 by 2, and we need to find the distance, velocity, and acceleration at time t equals 3 seconds. At time equals 0, or at initially, we have given the distance as naught, which is 3 meter. So we need to find distance, velocity, and acceleration at time equals 3 seconds, and we have given the expression of velocity. So it is pretty much easy to calculate the velocity at any time, because we have already given the velocity. So we can actually calculate the velocity at time equals 3 seconds. We just need to put here t equals 3, and we will get the velocity at time equals 3, because we have already given the expression of velocity, right? So velocity at time equals 3 will be 2 minus 4 multiplied by 3 plus 5 into 3 to the power 3 by 2. So it will be 2 minus 12 plus 5 multiplied by 5.196. This is minus 10 plus 25.98 will be 15.98 meter per second. So this is my velocity at t equals 3. We just substitute t equals 3 here in the expression because we have already given the expression of velocity in terms of time. So if we want to calculate the velocity at t equals at any t, 3 second, 4 second, 5 second, we just need to substitute the time accordingly and we will get the velocity at that time. Okay, then now how to find the, let's say, acceleration. So we have seen that acceleration is defined by dv by dt. It's a derivative of the velocity. So we can use this expression, we can actually take the derivative of this expression. So v is 2 minus 4t plus 5t 3 by 2. So it is 2 minus 40 plus 5t to the power 3 by 2. So we need to take the derivative of this. So it will be minus, it will be minus 4 plus 5 3 by 2 2 minus 1. So this is my acceleration. So when I take the derivative of the velocity, I will get the acceleration, which is minus 4 plus 15 by 2 into t to the power half. So at acceleration at time equals 3, we need to substitute this expression with time equals 3. So it will be minus 4 plus 15 by 2 multiplied by 3 to the power half. So my acceleration will be minus 4 plus 15 by 2 multiplied by 1.73. So it will be minus 4 plus 13. So this will come out to be 9 meter second to the power minus 2. So this is my acceleration. So we just use this expression which says that the acceleration can be defined as a rate of change of velocity in time. We have given the expression of velocity, so we use that expression and we differentiate this expression here, and we got the expression for acceleration, which is given in terms of time. So at any time you can find the acceleration. So we found the acceleration at t time equals 3 seconds, which is 9 meter per second square. Then we can use, to find the distance at time equal 3 seconds, we can use velocity, which is given as rate of change of distance with time. So my velocity is 2 minus 4t plus 5t to the power 3 by 2 equals ds by dt. 2 minus 4t plus 5t 3 to the power 2 dt, right? So this might be the expression. So we need to integrate it. Here s0 to s and here 0 to t. So LHS I am integrating distance from s0 to s, and we have given s0 in the question, which says that at initial time t equals 0 my s0 is 3 meter, and at RHS I am integrating with respect to time from 0 to t. So when I integrating left hand side, I will get 2t minus 4t square plus so this will be s minus s naught 2t minus 2t square plus 2t to the power 5 by 2. So my s naught is 3, so s will be 3 plus 2t minus 2t plus 2t to the power 5 by 2. So now we can actually find the distance at time t equals 3, because this s, the expression of distance given in terms of time. So when we substitute t, we will have 3 plus 2 multiply 3, this is t square, 2 3 to the power 2 plus 2 3 5 by 2. So it will be 3 6 18 plus 2 this will be 31.176. So this will be 22.176 meter. So this is my distance at time equals 3 seconds. So just to recap, we have given the expression of velocity, and which is given in terms of time, and we have been asked to calculate the distance, velocity and acceleration at time t equals 3 seconds. And we use the basic equations that we have discussed before this question to calculate. So since we have given the expression of velocity, which is a function of time, we can actually calculate the velocity at any time. So in the question we need to calculate at t equals 3 seconds. So we just substitute here t equals 3, and we actually got the velocity directly, which is 15.98 meter per second. So it is very easy, it is very straightforward problem to calculate the velocity, because the expression of velocity in time is already given. So you can calculate velocity at any time. Now to calculate the acceleration, we use the fact that acceleration can be given in terms of rate of change of velocity in time, which is dv by dt. So here we actually differentiate the expression of a velocity. We take the derivative of velocity expression, and when we do that, we can able to write the expression of acceleration, which is given in terms of time. So now we got the expression of acceleration as a function of time. So at any time we can actually calculate the acceleration. So at time equals 3 seconds, we just substitute the value of t, which is t equals 3 seconds here, and we got the acceleration, which is 9 meter per second square. Then we use the fact that velocity can be given in terms of change of distance and time, rate of change of distance and time, and we use this expression, we integrate to derive the expression of distance as a function of time, and then the same story, you can actually calculate this distance at any time. So at t equals 3, when we substitute time equals 3 seconds here, we actually arrive at the answer distance, which is 22.176, which means at time t equals 3 seconds, the body move to a distance 22.176 meter. Right. So as we discussed, we briefly discuss about the three equations of motion in case of constant acceleration. And here in this problem, you can see that the acceleration was not constant because it is a function of time here. Here it is a function of time. It is not a constant. So you cannot use these kind of expression which we have discussed, because these expressions are valid only for the constant acceleration. Because but since here the acceleration is changing with time, you need to use this standard relation, the acceleration which is the rate of change of velocity in time, and the velocity which is given as the rate of change of distance in time. So let's move to the next question. So here a small projectile is fired vertically downward into a fluid medium with an initial velocity of 60 meter per second. Due to the drag resistance of the fluid, the projectile experiences a deceleration A, which is given minus 0.4 v cube meter per second square, where v is in meter per second. Determine the projectile velocity and position 4 seconds after it is fired. So again, when we see this question, one thing is clear, that acceleration is not a constant. It is given in terms of a velocity. So we cannot use these relations. And so on. Because in this relation, acceleration should be a constant. But in the question, acceleration is given as a function of velocity which is changing. The velocity is changing. The initial velocity is 60 meter per second, which is v naught is 60 meter per second, and v is some velocity at some time. And we need to find the velocity and position at time equal 4 seconds. So at time equal 4 seconds, we need to find the velocity and we need to find the acceleration also. So if we use the expression that acceleration can be given as rate of change of velocity, which is a general expression, whether acceleration is constant or not, you can always use this expression, this and this one, the velocity which is given as the rate of change of displacement in time. So when we use this expression, we can write as dv equals a dt. You have to integrate from v0 to v and from 0 to t. So acceleration we have given, which is minus 0.4 v cube dt. So when we simplify the above expression here, I will get dv divided by v cube equals minus 0.4 dt. Here I am integrating from 0 to t. So you can see now it become a purely mathematical exercise, because the only concept that we need to concern about is this expression, the acceleration which is rate of change of velocity in time, and this expression which is velocity or rate which is given as the rate of change of displacement in time. Once you use this expression, you can see now it is all a mathematical exercise. So the concept is very easy to understand. So now you have to integrate this expression. You can even write this as here 0.4, this could be minus, so this will be just positive dt. So when you integrate it, you will get t equals 1 by 0.8 1 by v square minus 1 by v naught square, and v naught is given, which is 60 meter per second. So this will be 1.25 1 plus 1 by v square minus 1 by 60 square. So we need to find the v in terms of t. So we will have we can write down the expression of velocity in time. So at any time we can then find the velocity. So here v can be written as this could be my v. So you can see this v, which is coming from this, can be written in terms of time. So it is keep changing in time. So if we want to find the v at time equals 4, we need to substitute t with 4. So v will be so v at time equals 4 will be given as 0.558 meter per second, right? So at initial time t equals 0, my velocity was 60 meter per second, but at time t equals 4, my velocity reduced to 0.558 meter per second. So we have calculated the velocity. Now we need to calculate the position. So for position, we can use the fact that velocity can be given as rate of change of position and time. So if I integrate this expression as from say 0 to s, ds, and here from 0 to t v dt, and we already know what is v, which is 1 by 3600.8 t. So basically we need to integrate this expression. And when we integrate it, we will get s, which is 1 by 0.4, 1 by 3600 plus 0.8 t to the power 1 by 2 minus 1 by 60. So when we substitute t equals 4 second here above, we will get s 4.43 meter. So just to recap here, we have given the acceleration and the initial velocity, and we need to find the velocity and position at some certain time, which is 4 seconds. So our standard relations are that we have to use is velocity, which is given by rate of change of position in time, and acceleration, which is given by rate of change of velocity in time. These two expressions. So first we use this expression to integrate. We have already given the expression of acceleration, which is minus 0.4 v cube, and using this, when we integrate, we can able to find the expression of velocity, which is in time. So at any time you can find the velocity. So at time equals 4 seconds, we found that the velocity is 0.558. You just need to substitute the time here, that's all. And then we use the fact that the velocity can be given by rate of change of position and time. So again we integrate, we found the expression of position and time. So at any time we can find the position. So at time equals 4 second we got the position 4.43 meter. So even in the previous question we have used these two relations. So these two relations are the general relation. So whether acceleration is constant or not, you can actually use this relation to find the suitable quantities. So here we need to integrate it. Suppose we have to find the velocity and we have given the acceleration. Sorry, we have given the velocity. The velocity is given in time and we have to find the acceleration. Then using this expression you can actually just take the derivative of the expression of velocity and find the acceleration. But you have given the acceleration, so you rearrange this equation like this and integrate it. Similarly, here you have given the velocity and you need to find the position, so you rearrange the equation here like this and take the integral. If you have given the position but you need to find the velocity, then you can just substitute the expression of position here, take the derivative, time derivative, and you will get the velocity expression in time or some expression of velocity. So you can see using this two relation only will solve the problem, at least in the kinematics or the problem type of problem we are solving. So these two concepts you need to understand, and rest you can see it is just a mathematical build up, that's all. So let's solve a similar problem once more. So here we have given the acceleration of point A, which is defined by the relation minus 1.8 sine kt. A and t are the expressed in meter per second square and seconds. Basically they are acceleration and time. And k is 3 rad per second. Knowing that x equals 0 and v equals 0.6 meter per second at t equals 0, determine the velocity and position at time 0.5 seconds. So it's a similar problem. We have given the expression of acceleration, which is 1.8 minus 1.8 sine kt, and we have given the initial velocity at time t equals 0, which is 0.6 meter per second, and we need to find the velocity and position. And we will be doing the same thing. First defining the acceleration, which is rate of change of velocity and time. We need to find the velocity, so I can write this expression as dv equals a dt, taking the integral. So I'm taking the integral from v0 to v, and here 0 to time. I'm taking v0 here because we have given the v0. So this is my v0, which is 0.6 meter per second. So my LHS will be v minus v0, and my RHS will be 1.8 sine kt dt. So when you take the integral, v0 is 0.6, you will get 1.8 divided by k cos kt. So it will be 1.8 k cos kt minus 1. So v equals 0.6 plus 1.8 divided by k cos kt minus 1. So this is my expression of velocity in time. So now at time t equals 0.5 seconds, you need to find the position and velocity. So when we substitute t equals 0.5 second here, and k is given, which is 3 rad per second, you will have v, which is 0.6, 1.8 by 3 cos 3 multiplied by 0.5 minus 1. So you can find the velocity as 42.4 millimeter per second. Right, it's a same problem. We have been using the same method. Now we can use another expression where the velocity can be defined as rate of change of displacement in time. So this expression can be written as ds equals v dt, and we need to take the integral. Okay, we have given the distance initially, which is x equals 0, so it will be 0 to s, and this will be 0 to t. So this will be, when you integrate the left hand side, you will get s, and you already know v, which is this. Right, so when you take the integral, you will get 0.6 t. Right, so this will be 0.6 t plus 1.8 sine kt by k square minus 1.8 t by k. So this is the expression of s. So at t equals 0.5 seconds, you just need to substitute t equals 0.5, and when you do that, you will get s as 200 millimeter or 0.2 meter. So just to recap, we have been given the expression of acceleration and some initial information like the velocity at initial time, which is 0.6, and distance initially is 0, and we have to find the position and velocity at time t equals 0.5 seconds. So again we use this expression, which we modified. We write like this, and we use the expression of acceleration, and then we integrate it, and we can able to derive the expression of velocity in time. So at any time you can find the velocity. So at time t equals 0.5 second, we found the velocity, which is 42.4 millimeter per second. Then we use this expression again. So you can see that again and again we are using only two expressions. So only two expression we are using. So here v equals rate of change of distance and time. We rearrange this equation, take the integral, and write down the expression of distance, which is given in terms of time. So at any time you can find the distance. So at time t equals 0.5, you will get distance, which is 200 millimeter. So we have solved three problems, and all those three problems are similar in nature because we are using only two expressions. Either it is velocity, which is given as rate of change of distance in time, or acceleration, which is rate of change of velocity in time. And using this only, we are solving for velocity, acceleration, and position at some later time. So let's move to the next question. So for a short time, the path of a plane is described by y equals 0.001 x square. If the plane is rising with a constant velocity of 10 meter per second, determine the magnitudes of the velocity and acceleration of the plane when it is at y equals 100 meter. So here the plane is moving, and it is moving in the xy plane, which is given here. So this is my x-axis and this is my y-axis. So as the plane is moving, it is actually tracing out a curve. So this is my plane which is moving, and it is tracing out a curve, and this curve can be given by the expression y equals 0.001 x square, and it is given that, so velocity and acceleration, these are the vector quantities. So you can write velocity as vx plus vy. Similarly, acceleration can be written as ax plus ay. So ax is the x component of acceleration, ay is the y component. Similarly, vx is the x component of velocity, and vy is the y component of velocity. So here it is written that it is rising with a constant velocity of 10 meter per second, which means vy is 10 meter per second. It's a constant. It's a constant. Vy is not changing. It is a constant, which means my ay should be 0, because my ay is a rate of change of dy with respect to time. And since vy is 10, it is not changing. It is always 10. The derivative of 10 or any scalar quantity is 0, right? So my ay is 0. Similarly, we will have some vx, and ax can be given as rate of change of vx and time. So we don't know what is vx, and therefore we don't know what is ax. So we need to find the velocity and acceleration, magnitude of velocity and acceleration when y equals 100 meters. So in earlier problem, we have to find the velocity, acceleration and position at some time t. Now here we have to find the same thing at some spatial location, which is y equals 100 meter. And we have to find the magnitudes of velocity and acceleration. So magnitude can be given as vx square plus vy square whole root. This is the magnitude of velocity, and magnitude of acceleration is ax square plus ay square under square root. Because v and a are the vector quantities, so for any vector, the magnitude of that vector can be given by this expression. So here we need to find vx, vy, ax and ay. So when we find these four quantities, we can able to find the velocity and acceleration. We already know vy, which is 10 meter per second, and since, as we discussed, vy is constant, it is not changing in time, my ay, which is given by rate of change of vy, is 0, because rate of change of vy is 0. I mean, the vy is constant, therefore there is no rate of change of vy. Basically, you are taking the derivative of a scalar quantity, which is 10, and which should be 0. So my ay is 0. So out of these four quantities, two quantities we already found, which is vy 10 and ay 0. Now we need to find vx and ax. And we have given the trajectory of the plane, which is y equals 0.001 x square. Okay, so you can see that as y changing, my x is also should change, or if my x changes, my y should change. And we need to find the magnitude at y equals 100 meter. So what is the corresponding x value? Because you can see in this trajectory, so this is my trajectory of the plane, which is given by y equals 0.001 x square. This is x and this is y. So you can see as my y is changing, or as my x is changing, I'm going toward right hand side. As my x is changing, my y is also changing, right? So what is the value of x at y equals 100? Because we need to find the velocity and acceleration at y equals 100 meter. So what is the corresponding x value? So at y equals 100, let's say here my y equals 100 meter. So what is this x value? So for that we will use this equation. So my x will be 316.22 meter. So this is my value of x at y equals 100 meter. So when the particle reaches y equals 100 meter, it will cover the distance x, which is 316.22 meter, right? So we have already known about this. So let's try to find unknown, which is Vx and Ax, from the known quantity. So my Vy, so as we discussed earlier, like my Ay can be given as rate of change of velocity in the y direction, and since my Vy is 10, which is a constant, my Ay is 0. Similarly, I can use Vy as rate of change of y in time. So my Vy is y, I can write as 0.001 x square. So this is 0.001 x square divided by t. So y and x both are function of time because they are changing in time. So this can be written as 0.002 x dot. So if my Vy, which is dy by dt, my Vx will be dx by dt. My Ax will be dvx by dt. My Ay will be dv by dt, which is 0. So this quantity is actually dx by dt, right? Because it's a x dot means the x is changing in times. It's a derivative with respect to time. So I can write my Vy as 0.002 x Vx. So Vy is 10.002, and I already know x at y equals 100 meter. My x will be 316.22, so it's 316.22 Vx. So I can find Vx here. So it will be 0.002 multiplied by 316.22. So my Vx will be 15.81 meter per second. So we know Vx, we know Vy, we can actually calculate the magnitude of velocity. Which is 18.717 meter per second. So this is my magnitude of velocity. Similarly, if you want to find the magnitude of acceleration, we have already know Ay square, which is 0. We need to find Ax. And to find the Ax, we can actually use this relation. So my Ay equals dvy by dt, and dvy by dt is, so this is my Vy, right? This is my Vy, which is written in terms of 0.02 x Vx. So it is 0.002 x Vx divided by dt. And this is my Ay. This is Ay equals to derivative of 0.002 x Vx. But my Ay is 0. So this is 0 equals derivative of 0.002 x Vx. So this will be 0 equals, so both x and Vx are a function of time. So it will be 0.002 x dot Vx plus 0.002 x V dot x. And we have already discussed that my Vx will be dx by dt, Ax will be dvx by dt. So this quantity is Vx and this quantity is Ax. So it will be 0.002 Vx square plus 0.002 x Ax. We already know Vx square, which we found as 15.81. So 0 equals Vx square plus x Ax. So my minus x Ax equals Vx square. Ax will be Vx square divided by x minus. So it will be 15.81 square divided by x, which is 316.22. So my Ax will be 0.79 meter per second square, and it is in minus. So you can see that my magnitude of acceleration is Ax square plus Ay square, but my Ay is 0, so my magnitude of acceleration will be Ax square. So this will be Ax. So this will be my magnitude of acceleration also, 0.79 meter per second square. So conceptually, this problem was actually much more involved problem. So in earlier three problems, we just used the basic concept that the velocity can be given by rate of change of displacement in time, and acceleration can be given by rate of change of velocity in time. But in this problem, we have to use a more conceptual knowledge. So here we have given the path y equals 0.001 x square, and we need to find the velocity and acceleration when y equals 100 meter. So at this y, we actually use this expression to calculate its corresponding x, because as the particle is rising, and let's say here it is reaching y equals 100 meter, then what is the corresponding value of x? And we found that it is 316.22 meter. Then since velocity and acceleration are the vector quantities, it has x component of velocity and y component of velocity, and similarly with acceleration, it has both x and y components. So here, using this expressions only, you can write Vx as ds by dt, Vy as dy by dt, Ax can be written as dvx by dt, and Ay is dv by dt. We are using only these two concepts. And in the question, we have given that Vy is constant, which is 10 meter per second. So from this, we found that Ay is 0 because the rate of change of Vy is not there. It is a constant. It is 10 meter per second and always remain 10 meter per second. But now to find the magnitude, we record Vx and Ax to find. We already know Vy and Ay, which is 10 and 0 respectively. So we use the known result to calculate it. To calculate the Vx, we use this expression Vy equals dy by dt, because we know that y is written in terms of x. So this is advantage for us. So when we write dy by dt, which is my Vy, I can write this y in terms of x. And since x and y both are a function of time, then when we take the derivative of this expression, we will write the expression of Vy in terms of x dot. and x dot is basically dx by dt, which is my Vx. So I can find Vx here. Similarly, I can use this expression, which is Ay equals dy by dt equals 0. So I can use this expression, and Vy can be written in terms of x and y, because we already found Vy from the earlier calculation. From this calculation, we already found Vy, and hence from this expression we can able to get Ax, which is this. So this is my Vy, which is 0.002 x Vx. When we take a time derivative, we will get this. So x dot is Vx, so it will be Vx square, and Vx dot is Ax. So I can write v dot x as Ax, and we can calculate Ax, which we calculate as 0.79. So then we can calculate the magnitude of velocity and acceleration. So even in this question we have used the same concept. It is actually much more involved. So this was a pretty difficult problem, but this is to just understand the concept, because when you solve the difficult problem, you will go much more deeper into the concept. So let's solve one more problem here. So here we are given the position of a particle, which is defined by a displacement vector. Here t is in second, and determine the magnitude of velocity and acceleration at time equals 1 second. So as we discussed, the magnitude of velocity and acceleration is given by Vx square Vy square whole root, and the magnitude of acceleration will be Ax square Ay square and its whole root. The velocity vector can be given as Vx and Vy, which is the y component, and acceleration vector is Ax and Ay. So we have given the displacement vector, right? So you need to identify that there is a difference between distance and displacement. So distance is a scalar quantity. It can be represented, let's say, by s. So it's a scalar, whereas the displacement is a vector quantity, and it can be defined by vector, which is x and y component, having the x and y component when you consider 2D geometry. And we will actually talk about this difference much more better way in this question. So in this question you have to find the distance and displacement, so you can actually see how they are different with each other. So until now we have given here the displacement vector, which has both x component and y component, and we need to find the velocity and acceleration. So we have given the vector, so the velocity vector can be given as rate of change of displacement vector with time. So in the above expression we have used the same expression of velocity. We have used the same expression of velocity, but for the scalar quantities. Right? For the scalar quantities, we have used this problem. Yeah, you can see that here the Vx can be given as dx by dt and Vy can be given as dy by dt. But now we are using the same concept for a full vector. It's a rate of change of full displacement vector in time. So this can be a velocity vector, and the acceleration vector can be given as derivative of velocity vector in time. So the velocity vector is actually given as 5 cos t, 5 cos 2t in x, which is the x component, and 4 sin 2t, which is the y component. and we have to take the derivative of this. So this will be, when we differentiate this, it will be minus 10 sine 2t in x, which is x component, plus 8 cos 2t, which is the jth component. So the outcome is also a vector which has a 2 component. So this is my Vx and this is my Vy. So Vx is 10 sine 2t. So in order to calculate the magnitude, we need to calculate Vx and Vy. And we need to calculate Vx and Vy at time equal 1 second. So at time equal 1 second, it will be sine 2. Similarly, Vy is 8 cos 2t, and at time t equals 1, it will be 8 cos 2. So the velocity, magnitude of velocity will be Vx square plus Vy square. So it will be minus 10 sine 2 square plus 8 cos 2 square. So when you solve this, you will get the magnitude, which is 9.68 meter per second. So this is the magnitude of this velocity vector. Similarly, you can find the acceleration. So you have this velocity vector, so you can use this velocity vector to find the acceleration. So the acceleration vector can be given as rate of change of velocity vector in time, and we know what is the velocity vector, which is minus 10 sine 2t in the x direction and 8 cos 2t in the jth direction. When you take the derivative of this, you will get minus 20 cos 2t minus 16 sine 2t. Right, so this is my ax and this is my ay. So ax at time t equals 1 will be minus 20 cos 2. Ay at time equals 1 will be minus 16 sine 2. And the magnitude of a, or the acceleration vector, will be x square plus ay square whole root. So it will be minus 20 cos 2 square plus minus 16 sine 2 square. And when you calculate this, you will get 16.8 meter per second square. So here you have given the displacement vector, and you need to find the velocity and acceleration, magnitude of velocity and acceleration. So since you have given the displacement vector, it is pretty much straightforward to find the velocity and acceleration vector. So it will be, velocity vector can be defined as the rate of change of displacement vector, and acceleration vector can be given as the rate of change of velocity vector. But you need to find the magnitude of acceleration and velocity vector, which can be given by these expressions. Basically, you need to find the component of velocity and acceleration. So when you take the derivative of displacement vector, you will get the velocity vector. So this x component is actually the Vx and y component is actually Vy. Then you can, at any time, you can calculate Vx and Vy and then the magnitude here. Similarly, if you take the derivative of velocity vector, you will get the acceleration vector and hence the component of acceleration. Here it is ax and this is ay. Then when you find out the ax and ay, you can actually easily find the magnitude of acceleration, which is 16.8 meter per second square. So let's move to the next question. So here the car travels from A to B, then B to C. As shown in figure, determine the magnitude of displacement of car and distance traveled. So this is a very good problem to understand how distance and displacement are different and how they are different. So in this problem, the car is traveling from point A to point B and then point B to point C. So earlier we discussed that we need to find displacement and distance from point A to point C. So earlier we discussed about distance, displacement and distance very briefly. So displacement is a vector quantity and distance is a scalar quantity. So how you calculate the distance and displacement here? So just to recap here, car at point A is traveling to B and then it is traveling to C. And let me define the coordinates. So this is my x, this is minus x, this is y, and this is minus y. So distance you can easily calculate because it is a scalar quantity. So you just need to add various distances, various pieces of distances. So for example, let's say first cars travel from point A to point B. So what is the distance it traveled? It traveled 2 kilometers from point A to B. So point A to B, it travels 2 kilometers. Then from point B to point C, it traveled 3 kilometers. So what is the total distance car traveled? First, it is traveling from A to B 2 kilometers, then B to C, which is 3 kilometers. Then the total distance car travels is 5 kilometers, which is a no-brainer, which is very easy. Anyone can actually calculate this. So the total distance is 5 kilometers. This is my distance. And since it is a scalar quantity, it can be defined by a scalar magnitude only. It can be defined only by magnitude, which is 5. So distance is 5 and it is a scalar quantity. But then how to calculate displacement? So for displacement, you need to first so the initial position was point A and final position was C. So displacement is, so this is my distance traveled from A to B plus from B to C. So this is my distance which I am showing by blue color. Whereas displacement is actually relate the initial position and the final position. And it is a vector quantity. So what is my how you define the vector quantities? So in earlier problem we have defined the displacement vector as x, magnitude x in the horizontal direction and y in the vertical direction. So this magnitude in the horizontal direction and magnitude in the vertical direction constitute a vector relation. So we need to calculate x and y at point C. So at point C you can see that my x is 2, the magnitude of x is 2 and the magnitude of y is 3. So it can be written as, my displacement vector can be written as 2 in the x direction, and since it is going down, the car is going downward, it is going in the minus y direction, so it is minus 3. Because it is a vector quantity, so you need to take care of minus and plus. So for distance, this was not the case. So all the quantities was positive because we don't need to consider direction. So we just need to consider all quantities as positive. But here you need to consider direction, and you see that car is moving in the minus y direction. So this is minus 3 j cap. So this will be my displacement at point C. So you can see you are actually relating, displacement vector is actually relating the initial position to the final position, and you are calculating the magnitude from the initial position. So first x magnitude is 2 in the positive x direction, the magnitude is 2. Then in the y direction you can see the magnitude is minus 3. It is moving in the minus y direction, so the magnitude is 3 in the minus y direction, so it is minus 3. So this is my displacement, which is a vector quantity. You can write down in a vector form, whereas the displacement is a scalar quantity, so it is just a 5 kilometer. So you can see how the distance and displacement actually are different in each other, with each other. So let's solve a similar problem. Here. So here a particle travels from curve A to B in 1 second. If it takes 3 seconds for it to go from A to C, determine the average velocity when it goes to B to C. So particle take 3 seconds from A to B. It takes 1 second, and to move from A to C it takes 3 seconds. And we need to find the average velocity when it goes to B to C. So my average velocity vector can be given as displacement vector with respect to time. So for the velocity from B to C, I need to consider the displacement from B to C, right? Because I need to calculate the average velocity vector from B to C, which means this displacement should be B to C. So I can write this displacement vector as AC, and which is minus displacement vector AB, right? So basically AC minus AB, which will give me displacement at BC, right? It is very straightforward. So now I need to calculate the displacement vector AC and AB. So what is my displacement vector AC? So this is my initial position. We have already given x and y coordinate. This is my initial position. So x, when it reaches C, what is the magnitude? So this is 20, and this is also 20. So at C, what is my magnitude of? So as I said in the previous question, my displacement magnitude can be have this form: magnitude of x and magnitude of y in the vertical direction, magnitude of x in the horizontal direction and magnitude of y in the vertical direction. So what is the magnitude of x? It is plus 40 because it is in the positive x-axis. So it is plus 40 I cap. And what is the magnitude of y? So you can see from A to C, it is not moving in the y direction. It is only moving in the x direction. So it is 0. So basically my displacement vector AC is 40 I. Then let's find the displacement vector BC. So basically from initial is A and my final is now B. Sorry, this is AB. Initial is A and final is B. So now you can see what is the magnitude of x distances traveled. It is 20, positive 20. And what is the magnitude of y? It traveled vertically. It is again 20. So this is also 20 plus 20j. So this is my displacement vector RAB. So as I said in the previous question, it relates initial position to final position. So here initial position is A, final position is B. In case of RAC, my initial position is A and the final position is C. So these two are my displacement vector. Now I can use this relation to find the average velocity. vector. So my RAC is 40i minus 20i plus 20j divided by delta t. So delta t is 3 seconds. So you can actually subtract I component with each other. You cannot subtract I component with j component. It's a mathematical rule for addition and subtraction of vector. You can only subtract and add I and I component, and j component. So here this will become 20i plus 20j divided by 2. So my average velocity vector will be 10i plus 10j. This is my answer. So in this problem, we just need to determine the displacement. So we determine displacement AC and displacement vector AB. So you just need to concern about the initial and final position. So when you define the displacement vector AC, the final position is C, and you need to define the magnitude of X and Y. So magnitude of horizontal position and magnitude of vertical position. So at C you can see the magnitude of horizontal position is 40 in the positive x-axis, but there is no motion in the y direction. So your displacement vector will be 40 I cap, but for RAB the horizontal position is 20 I and the vertical position is again 20 j. So the vector will become 20 I plus 20 j. So once you define the vector displacement vector, it is very easy to calculate the average velocity. So until now we have discussed the problem which are mostly based on the Cartesian coordinate. So now we will move to the problems where we will discuss the same concept but in curvilinear coordinates and in polar coordinates. So in the Cartesian coordinate we have given the displacement vector which is given by xi and yj, and the velocity vector is the derivative of displacement vector and it is x dot I plus y dot j. My acceleration vector is the derivative of velocity vector and it is x double dot I plus y dot j, or it can be vx dot I plus vy dot j. But these equations are valid for the Cartesian coordinate system. But when we concern about the curvilinear coordinate system or in the polar coordinate system, apart from the magnitude, so here you can see the magnitude is changing in time, x dot and y dot, but in the non-Cartesian coordinate, this direction is also changes in time, that we will see. So in the curvilinear coordinate, like in the Cartesian coordinate, we actually define the direction in terms of x and y. In the curvilinear coordinate, we actually define the direction by t, which is the tangent direction, and n, which is the normal direction. So t is the tangent direction from this point of this curve, and n is the normal direction of this point to curve. So this is my t at this point, which is tangent to this curve, and n is the normal to this curve. So we will define the velocity and acceleration in tangent direction as well as in the normal direction. So let's say we have a point here which is C. Let's say this is point A, this is point A dash, and there is a curve, and this is the angle which is d beta. This is rho. So rho is the radius of curvature. This is the direction en, and this is my et direction, and this curve has displacement which is ds equal rho dB. So my rate of change of displacement from point A to A dash is ds, which is rho d beta, and rho is the radius of curvature, beta is the small angle. So my velocity can be given as ds by dt. So s is rho dB, and assuming that my radius of curvature is constant when it is moving from point A to A dash, it will be rho d beta by dt, and since my radius of curvature is constant, it will be d beta by dt, which is rho beta dot. This is my velocity. This is my velocity in the tangential direction. Now what is the acceleration? Acceleration will be given as velocity vector divided by time, and my velocity is given as VET dt. So here, unlike in the Cartesian coordinate system where we define the acceleration as change in magnitude, here it is also given in terms of change in direction. So if I take the derivative, we will get v dot et plus v et dot. So this part will give you change in magnitude, acceleration due to change in magnitude, and this part will give you acceleration due to change in direction, because the direction et is changing. Right, so let's say you have here et vector, and this is changed to, let's say, et dash, and this is the change which is det. This is small angle d beta. So here the change in et can be given as en d beta, because this direction det, this direction is en, because it should be normal to et, right? So the normal to et is en, which is this direction, and here en and the direction of en and det is same, so I can write det as en multiplied by d beta. It's a magnitude d beta. It's a change in by d beta and the direction of en. So basically what I'm saying that d eta has a direction of en and having some magnitude here, that how much it is changing, and it is changing by d beta. So this will be d beta. It is like saying you have a velocity vector v. Let's say you have only x component of velocity vector, so this is your x component that changing. Let's say that I have a velocity vector which is changing only in the x direction. So I can write this velocity vector as ex and vex. So here v is the magnitude of this velocity vector and ex is the direction of this velocity vector. Similarly, my direction of det, as you can see here, it is changing in the en direction. So it has the en direction, and how much it is changing? It is changing by d beta, because if you increase the d beta, it will increase accordingly. If you increase at higher rate, det will increase much more. If you increase at lower rate, det will increase at a lower rate. So this is the magnitude of it. Now if you take a time derivative of this, you will have et b dot en. So now you can use this here. So my acceleration will be v dot et plus v et dot. So now you can use this here. So you will have v dot et plus v et dot, which is beta dot en. And we know what is v dot is. Sorry, we know what is v is. So v can be given by rho b dot. So this can be written as v square by rho en plus v dot et. So this is the normal component of acceleration, and this is my tangential component of acceleration. So my normal component of acceleration is v square by rho, and I can also write this as rho b square, beta dot square, or v beta dot. Basically what I am doing is I am using this expression rho b dot here. So you can write this as rho b dot square or vb dot. So this is the normal component of acceleration, and this will be your tangential component of acceleration, which is v dot or s double dot. So you can see the acceleration is changing not only by magnitude but also due to changing in the direction of tangential unit vector. So now we will be using these equations, this equation to find a and this equation to find v to in the curvilinear coordinate. So let's solve one problem. Determine the maximum constant speed a race car can have if the acceleration of the car cannot exceed 7.5 meter per second while rounding a track having a radius of curvature of rho. 200 meters. So rho is 200 meter, and we need to find the velocity where the acceleration is given as 7.5 meter per second square. So here it says that the velocity is constant, and we discussed that acceleration is due to rate of change of velocity and rate of change of direction of unit vector. The velocity is constant, so this component, tangential component, will be 0. So the acceleration can be given by v e dot t, and we just saw in the derivation here e dot t can be given in terms of normal direction. So it can be given right in terms of, so this component is actually the normal component, because e dot t can be written in terms of a normal component. Rate of change of tangential unit vector can be is in the direction of a normal component. So basically we are talking about the acceleration of a normal component. So this acceleration is the normal component, which is v square by rho, which we have already defined, v square by rho or v dot beta dot. We have already given rho, we have given an, we need to find v square or v. So v square will be an rho, so v will be root an rho. So v is an, which is 7.5 multiplied by rho, which is 200 root. So my v will be 38.729 meter per second. So it was a pretty much easy problem. We have given a radius of curvature, we have given the acceleration, and we have given a condition that it's a maximum constant speed. So maximum constant speed, so which means that we can write down the, so from the acceleration expression we know that it is due to the change of magnitude and change of direction. Since it's a maximum constant speed, there is no change of magnitude, so my acceleration, so the rate of change of magnitude can be given by the et component, and the rate of change of direction can be given by en component. So rate of change of magnitude is constant, which means my et component 0 is 0, and now the acceleration can only be defined in terms of en component or the normal component. So the normal component of acceleration is v square by rho. So my v will be then can be given by a multiplied by rho under root. So let's solve one more problem here. So here the truck travels in a circular path having a radius of 50 meter at a speed of v equals 4 meter per second for a short distance from s equals 0. Its speed is increased by v dot 0.05 s meter per second. Determine its speed and magnitude of acceleration when it is moved to s equal 10 meters. So such problem we have solved in the Cartesian coordinate, but now we have to solve a similar problem in the curvilinear coordinate. So we need to find the magnitude of acceleration. So we have solved the magnitude of acceleration problem in the Cartesian system, and it is given as ax square plus ay square under root. But in curvilinear coordinate, the magnitude of acceleration is given by at square plus an square. So basically we need to find at and an. We have given a speed of 4 meter per second here, and we have given that the speed is increased by v dot, which is 0.05 second meter per second square. So from the acceleration equation we have given that the acceleration vector can be given as by this relation which we have discussed here above. So the tangential component can be given by v dot and the normal component can be given by v square by rho. So this is the tangential component of acceleration, which we can find when, so v dot is the tangential component of acceleration, which is 0.05 s. So when we substitute s equal 10, we will get 80 for the tangential component of acceleration. But how to find the normal component of acceleration? So for that we will using the relation VdV equals AdS. We have to integrate this. So we have to integrate from 4 to V, and this we have to integrate from 0 to 10. And acceleration, the tangential component of acceleration is 0.05 s ds. So this will be v square by 2 from v to 4, and this will be 0.05 s square by 2 from 0 to 10. When we solve this, we will get v equals 0.583 meter per second. So this is the velocity at s equal 10 meter, right? So my normal component of acceleration will be v square by rho. Rho is 50 meter here. So my an is 4.583 square by 50. So when you solve this, you will get 0.42 meter per second square, and at is v dot, which is 0.05 multiplied by s. So at s equal 10, you will have 0.05 multiplied by 10, which is 0.5 meter per second square. So now you have AT and you have AN, so you can actually use this relation to find the magnitude of acceleration. So it will be A 0.5 square plus 0.42 square. So here when you solve, when you calculate, you will have 0.653 meter per second. So this is the magnitude of acceleration. So this type of problem we have solved earlier, but for the Cartesian. In the curvilinear coordinate, my magnitude of acceleration can be given by AT square plus AN square. So we need to find the tangential and normal component of acceleration. So whenever you are solving the acceleration and velocity for the curvilinear problem or for the polar problem, the easy way is to write first the expression of velocity and acceleration vector. So you see that my acceleration vector can be given by v square by rho in the normal direction and v dot in the tangential direction, and we have given the v dot, which is the acceleration in the tangential direction, which is 0.05 s. So we can find AT directly from this relation. Then we use this kinematics relation to calculate the velocity at later when the distance is s equal 10 meter. So at distance s equal 10 meter, my velocity come out to be 4.583 meter per second. Then for the normal component, this is my normal component of acceleration, v square by rho. I already got v, I already know rho, so I can actually calculate the normal component of acceleration, and this is my tangential component of acceleration, v dot, which is given in the question, which is 0.05 multiplied by s. So here I can find the tangential component. Once we got the normal and tangential component, we can actually find the magnitude of acceleration. So it's a pretty straightforward problem. So the next problem is also very same. It's the same problem. Here we have given the tangential component of acceleration, and we have to find the magnitude of acceleration. So you already have tangential component. You need to find the normal component of acceleration, and here you also need to find the velocity component. So you can find the tangential velocity component that we have discussed. So for that you can use the relation AT equals dv by dt. So dv will be a dt when you integrate it. So AT you already know, which is given by this relation. It is 0.5 e to the power t. So from that you will get expression of velocity as a function of time. Once you get the velocity, you can find the normal component of acceleration and the tangential component of acceleration, which is given by this. And for the normal component of acceleration, you have already found the velocity, which is given as a function of time here, and rho is 5 meter. So from this you will get the magnitude of acceleration. And velocity you can find by integrating this quantity. So it's a similar problem that we have discussed until now. You can try this problem by yourself. So next week we will begin with solving the similar problem for the polar coordinates, and then we will move to the relative velocity and relative acceleration problems. So that's it for today. Thank you.